On this last video over power series, we're discussing this fact. It turns out that if you have a power series that's centered at 0 and it converges absolutely for whenever the absolute value of x is less than r, you can basically replace x with any continuous function, and the resulting series will converge whenever that function whenever the absolute value of that function is less than r. I think that's pretty cool. I wanted to show you just a couple of examples. So let's say we have this series. This is a very simple series. It's just x to the n. When n equals 0, we get 1. When n equals 1, we get x to the first. When n equals 2, we get x squared, and so on, x cubed, x to the fourth. The nth term is x to the n. Obviously, this is a geometric series because to get from term to term, I'm multiplying by x. 1 times x is x. X times x is x squared. Multiply that by x, you get x cubed. Multiply that by x, you get x to the fourth, and so on. So this is geometric. The first term is 1. The common ratio is x. So this converges to a, which is our first term, which is 1, over 1 minus r. Remember, you have a series that looks like this. It's a geometric series, and that's exactly the right form that we have. This converges to a over 1 minus r, the first term over 1 minus the common ratio, under the condition that the absolute value of r is less than 1. So this converges to 1 over 1 minus x whenever the absolute value of x is less than 1. So that's just a fact, and it's something that we studied previously, and it's a very simple example of that. Now, an example of this comes from taking that x and replacing it with a continuous function. I want to replace it with cosine of x. So I've got cosine of x raised to the n. So that's 1 plus cosine of x plus cosine squared x plus cosine cubed x, and so on. And the nth term is cosine to the n of x, or cosine of x raised to the n. That means the same thing. And according to this, this series will also converge whenever the absolute value of f of x is less than r. In our case, f of x is cosine of x, because I just replaced my x with cosine of x. That's f. So this converges, and because it's geometric, we know it converges to 1 over 1 minus the common ratio, which is cosine of x, as long as the absolute value of f of x is less than 1. Now we know that the absolute value of cosine of x is always between -1 and 1, except for certain values of x. So let's look at the cosine graph. We know it starts at its max, then it goes to 0, then it goes to its min, then back to 0, and then back to its max, and it just keeps repeating over and over again. So that's the basic cosine wave. So it looks like, well, we're going to have a problem at all of the multiples of pi, because at 0 we get 1, at pi we get -1, at 0 we get, or excuse me, at 2 pi we get 1. So obviously at the even multiples of pi we're going to have a problem, because that's when cosine of x equals 1. So that's an issue, because when cosine of x equals 1, we'd have 1 over 1 minus 1. We'd be dividing by 0, and we never want to do that. You know, you see those mushroom cloud things on Facebook, like those memes, and that's what happens when you divide by 0. Don't do it, ever. So Yeah, we're going to have a problem whenever x is an even multiple of pi, but also when x is an odd multiple of pi. Even when cosine of x is -1, I could put that in here and I'd get 1/2. But in that case, if cosine of x is -1, let's say x equals pi, this series does not converge. If cosine of x is -1, this is -1 to the n. So have 1 minus 1, plus 1 minus 1, plus 1 minus 1. So this will diverge in that case. But what this is saying is this will converge, or what this fact up here, what this fact up here is saying is that since this one converges whenever the absolute value of x is less than 1, this series converges under these conditions, then I can replace the x with cosine of x, and this series will converge under these conditions. And it's actually pretty simple. Let's do one more example like this. Let's see if I've got room on this other page. Yep, got some area to spare. So let's say you've got a function like this, and somebody asks you to find an infinite series representation or find an infinite series representing this function. F of x equals 4 over 3 minus natural log of x. Well, that actually looks a lot like a over 1 minus r, but r is not a constant times x minus a constant to some power like it has been in other problems. This time, the r of x is natural log of x. Well, that's fine. According to our theorem, natural log of x is continuous. So let's find a series representation for this. Now, in order to make this look like a over 1 minus r, I need to get rid of that 3 there. So I will divide the numerator and denominator by 3 to make it match our pattern. So I've got 4/3 over 1 minus 1/3 natural log of x. And through pattern matching, if I'm saying that that is a over 1 minus r, a must be that 4/3, and r must be the 1/3 natural log of x. Now, I should be able to write that as this infinite series, provided that the geometric series converges, where I would just replace this 1/3 natural log of x with x, and it does. So we get a times r to the n. Now, since this series converges, let's say this. So the exact same series, but I'm replacing that natural log, 1/3 natural log of x with just x. Since this converges, when the absolute value of x, that's our r value, is less than 1, this one also converges. Because this series is just like this series, I've just replaced the x with the 1/3 natural log of x. They're the same thing. But there are different conditions on this. See, I'm replacing that x with this. That fact I mentioned earlier says that this converges under this condition. Since this one converges when the absolute value of x is less than 1, this one will converge when the absolute value of 1/3 natural log of x is less than 1. Now, to get the interval of convergence, I need to write this absolute value inequality as a compound inequality involving x. So we know that if an absolute value is less than a positive number, that means the number inside the absolute value bars is between the positive version of that number and the negative version of that number. Because this is saying the distance from 0 of this number, the distance of this number from 0, is less than 1. And that distance is less than 0 when that number is between -1 and 1. So now we just want to get x by itself in the middle, so we'll multiply all three parts by 3. 3 times that 1/3 will just give us a natural log of x there. And then to get rid of this natural log of x in the middle, I'm going to exponentiate, because e and natural log are inverse functions, they undo each other. So we get e to the negative third is less than x, which is less than e cubed. So this converges, and it actually converges to this function here under those conditions. So what did the question ask us to do? It asked us to find an infinite series representing this, and we did. And usually we want to also find its interval of convergence. So here's our answer. F of x, which equals 4 over 3 minus natural log of x, can be written as this infinite series. Now it's not a power series. I want to call it a power series because that's all we've been talking about, but it's not a power series because these are not powers of x. But it is an infinite series. I wrote a 4 there instead of an n. Sorry about that. It is an infinite series. This is 4/3 times 1/3 natural log of x to the 0 plus 4/3 times 1/3 natural log of x to the first, and so on. Let's factor out the 4/3 from everything. So this to the 0 is 1. Then we get 1/3 natural log of x to the first, and then we take that and we square it, 1/3 natural log squared x, and then we take that and we cube it, 1 over 27 natural log cubed of x, and you keep going indefinitely. That infinite series represents this function when x is between e to the negative 3, so that's 1 over e cubed, and e cubed. And that is actually a property, this property right here. Where is it? There it is. This property right here is something we're going to take advantage of a lot in the next section when we learn more about a certain type of power series called a Taylor series.